Hello everybody, welcome into another lesson. So today we are going to start the geometry side of what we've been talking about. We are going to start talking about similar polygons. This will put ratios and proportion into application with geometry. So what does it mean for two polygons to be similar? I'm actually going to work backwards. For one, the corresponding angles are congruent. If we look at quadrilateral DABC and quadrilateral HEFG, you can see that corresponding angles between the two quadrilaterals are congruent. So one criteria is meant for these two quadrilaterals to be similar. Now, the other criteria is that the corresponding sides of each polygon are in proportion. So what does that mean to be in proportion? So let's compare DC to HG, okay? Let's compare DC to HG. If we look at that, you get the length of side DC is 20, the length of side HG is 30, which 20 to 30, that would reduce to 2 to 3. The ratio of two sides of a polygon that are in simplest form is called the scale factor. So this is called the scale factor. Scale factors are also quite useful. For example, let's say you wanted a toy replica of Buckingham Palace. It's going to be built based on scale factors because you certainly can't build a congruent model to Buckingham Palace. There's no way that would fit in your house or even your backyard. But a model of that would have a scale factor where you would have similar sides and length and height and angles and all that that would go into Buckingham Palace in a much smaller model. So the scale factor is the ratio of two sides in their simplest form. So basically, every side of one polygon compared to the other has the same scale factor. Okay, so what about DA? So on the left quadrilateral, DA will compare to HE, which would give you what? That would give you the ratio of 10 to 15, which also simplifies into 2 to 3. So far we have seen that we have two sets of sides in proportion, but they all have to be in proportion. Now what if we did AB to EF? If AB's to EF, that would be 14 to 21, which also reduces to a 2 to 3 scale factor. So far, 3 of the 4 sides actually have the same scale factor. Now, what about BC? Let's do BC to FG. Let's compare BC to FG. Do they have the same scale factor? Well, BC has a length of 8, FG has a length of 12, which also would give you a scale factor of 2 to 3. Alright, so in this case, all corresponding angles are congruent, and now all corresponding sides are in proportion. So both criteria have been met to determine that quadrilateral DABC is in fact similar to HEFG. And let me show you how you're going to write that in an abbreviated sense. There's a symbol for similar, as opposed to writing it out word for word. What you can say here is quadrilateral DABC is similar. That tilde, just that one tilde symbol means similar. It's similar to quadrilateral HEFG. G. So since both of these criteria have been met, we can now say that quadrilateral DABC is similar to quadrilateral HEFG. Now there's something else before we move on that I would like to point out. If your scale factor was 1-to-1, right? If it was 1-to-1, meaning that basically both sides have the exact same length at that point, in order to get a scale factor of 1-to-1, both sides of each quadrilateral, the corresponding sides would have to have the exact same length, therefore making the shapes actually congruent. So that proves that all congruent figures are similar, but not all similar figures are congruent. You see where I'm coming from? All congruent figures are similar because they have the scale factor 1-to-1 for every side, but not all similar factors are congruent. If there is any other scale factor other than 1-to-1, they're not congruent. They're just similar. So that's an important thing to keep in mind. Okay, so here's what we're going to do. There's no new theorems today, really. We're just going to do a few exercises here demonstrating our knowledge of similar polygons. So what we're going to do here, we're going to take 4 quadrilaterals. Well, let's see. I'm going to do them 2 at a time. B, C, D. Okay, so here's A, B, C, and D. And then I'll draw the next one. This is E, F, G, and H. Then let's go with what else they give us. That we do have 4 right angles. In each of these quadrilaterals, there are 4 right angles. So they're all 90 degrees. So what we need to determine is, between these 2 quadrilaterals, are they similar? We need to determine if they're even similar at all. Well, oh, I forgot to write down the sides. The lengths of the sides. 5, 5, 5, and 5. So this would make quadrilateral ABCD a square. So ABCD is actually a square then, since all the sides are congruent and there's 4 right angles by the definition of a square. And then you have EFGH, which 2, 4, 2, and 4. So EFGH would be a rectangle because you have 4 right angles, but only the opposite sides are congruent. So you have a square versus a rectangle, okay? Let's do the test for similarity. 1. Let's start with the angles. That's usually the easiest. If you look at the corresponding angles, well, all angles are right angles, so all angles are congruent. So if you went just based on angles, you could argue that they're similar. But that's not enough to say that all angles are congruent. All sides must be in proportion, have the same scale factor. So why don't we start with what we know here? Side DA. So let's take side DA to side HE, right? Those would be corresponding parts of the quadrilaterals. Well, side DA has a length of 5. Side HE has a length of 2, which would give you your scale factor of 5 to 2. So if you take the ratio of the other sides, in order for those to be similar, you should get the scale factor 5 to 2 for every single one of them. But let's compare AB of the left quadrilateral, the square, to the corresponding side of the rectangle, EF. Well, side AB has a length of 5, and then EF has a length of 4. Well, immediately we notice we don't have the same scale factor, 5 to 2 and then 5 to 4, between the two quadrilaterals. So these are not similar. They are not similar at all because their sides are not in proportion. They don't have the same scale factor for each set of corresponding sides. If they were to truly be similar, all the sides would either have to have the scale factor 5 to 2 or 5 to 4. One or the other. It can't be both. So they're not similar because the sides aren't in proportion. Alright, let's do a couple more here. We're going to determine if these are similar. Alright, this one is JKLM. Let's see what else they give us. Well, again here, we have 4 right angles for quadrilateral ABCD. And then we even have here, we have 4 right angles in quadrilateral JKLM. Each side of this quadrilateral to the left has a length of 5. So we have another square. Each side of this quadrilateral has a length of 3. We have yet another square. So we need to determine, are these two quadrilaterals, are quadrilateral DABC and MJKL, are they similar? Well, step 1, look at their angles. All angles are right angles, so all angles are congruent. So if all angles are congruent, then definitely the corresponding angles are congruent. So yes, that checks out. So step 1 checks out for them to be similar polygons. How about step 2? Are the sides in proportion? So let's take the corresponding side DA to this square and do it to MJ on this square. Take DA to MJ. We'll make those the corresponding sides. You would have the ratio 5 to 3, which means 5 to 3 is your scale factor. Alright, so that means now let's compare AB to the corresponding side of JK. AB and JK are corresponding sides. Well, that, again, that's going to give you 5 to 3. So far this is checking out. So far, yes, we've had 2 pairs of sides of each of the quadrilaterals that are in proportion. Alright, now what about BC? Let's do BC to the corresponding side here of KL. Well, BC has a length of 5, right? KL has a length of 3. Well, once again, you get the scale factor 5 to 3. And then last but not least, we need to take DC to the corresponding side ML. Well, DC has a length of 5. ML has a length of 3. Well, what do you know? All every side is in proportion. They all have the same scale factor between the two quadrilaterals. So yes, quadrilateral ABCD is similar to quadrilateral JKLM. So both criteria have been met. Corresponding angles between each of these two quadrilaterals are congruent, and then every single corresponding side between the two quadrilaterals are in proportion. In other words, they have the same scale factor. So quadrilateral ABCD is similar to quadrilateral JKLM. All right. Let's leave ABCD up there. I'm going to leave the square ABCD up there, but I'm going to draw a different quadrilateral here. All right, so how about, let's see. Quadrilateral NOPQ. What do they give us? They give us that every side has a length of 6, but here's a catch. This angle here is only 88 degrees. So let's look at this here. If we look at the sides of each of these quadrilaterals, it would look like they're all going to have the same scale factor, right? 5 to 6 for each set of corresponding sides. Okay, that's one criteria for determining similar shapes, but the other criteria also must be met that corresponding angles are congruent. Well, angle A would correspond to angle N. Clearly, angle A is not congruent to angle N because 90 definitely doesn't equal 88, right? So these are not similar right away because you have angles that are not congruent between the two. If you can prove even one set of corresponding angles between the two polygons is not congruent, then the whole thing's not similar. They all have to be congruent. So that one was actually pretty easy. All right, last one here. This time we're going to compare a previous exercise's one. JKLM. And let's go ahead here, set up what they gave us. And then each side here has a length of 3. Okay, so this time we're going to compare quadrilaterals JKLM and NOPQ. Looking at their sides, it looks like every single side would have the correspondence 3 to 6 between the two. In other words, the scale factor would be 1 to 2. But angle J, the corresponding angle to angle N, is not congruent. Angle J is not congruent to angle N because 90 definitely does not equal 88, right? So these two polygons are not similar. So in other words, in order for polygons to be similar, both criteria have to be met. That corresponding angles are congruent, and also that every single side between the two polygons, the corresponding sides, has to have the same scale factor. All right. A little bit different here. What can we talk about now? Alright, so we're going to have here two quadrilaterals. They start out by telling you that quadrilateral TUNE is similar to quadrilateral T prime, U prime, N prime, E prime. So we are going to be given two, not congruent, I said congruent, I'm sorry, they're similar. Quadrilateral TUNE is similar to quadrilateral T prime, U prime, N prime, E prime. And I'm going to draw those for you. We're going to do a few exercises with those. Alright, so what do we have here? Just drawing these two quadrilaterals so I can compare them. Okay, so we already know that these two quadrilaterals are similar. So here's what they give us. They give us that angles U prime and N prime are right angles. Whoops. Well, they would be because they're similar, but I looked at the wrong quadrilateral. It's actually, they only tell us here that angles U and N are right angles, but still, since they're similar, U prime and N prime would also be right angles. They give us TU has a length of 16. They give us that EN has a length of 28. Okay, they give us that T prime E prime has a length of 5K. They give us that E prime N prime has a length of 35. Then they give us that U prime N prime has a length of 15. Okay. So first thing we're going to do is find the scale factor. Since they're similar, that means they're going to have the same scale factor for every side. So find your scale factor. So to find your scale factor, we notice two sides have lengths, the corresponding sides between each of these quadrilaterals, EN to EN prime, E prime, N prime, both have lengths, right? So we're going to take that 28 and divide it by 35, which will be what? What's that going to simplify to? That would be 4/5. So the scale factor between the two polygons here, the two quadrilaterals, is going to be 4 to 5. So we identified our scale factor being 4 to 5. Now, we're going to find the measure of angle T. Oh, I did skip an angle, didn't I? Or the measure of angle T prime. Measure of angle T is 135 degrees, right? Next, we are going to find the measure of angle T prime. What is the measure of angle T prime? Well, if these two quadrilaterals are similar, we know what? That corresponding angles are congruent. So that could only mean that the measure of angle T prime would also be 135 degrees, since corresponding angles of similar polygons are congruent. So the measure of angle T prime would also come up 135. Okay. What else can we ascertain? What else do they want us to know? The measure of angle E prime. We have to find the measure of angle E prime. Well, here's one thing. We don't even know the measure of angle E, do we? So how in the world are we going to find E prime? Well, first we're going to find angle E. Let's find angle E. So we know for sure, since this is a quadrilateral, that the measure of angle E plus those two 90-degree angles plus the 135-degree angle are equal to 360, right? Well, so what this would turn into then is that the measure of angle E, so then you'd have 180 plus 135, that'd be 315. The measure of angle E plus 315 would equal 360, which could only mean that the measure of angle E itself would be equal to 45 degrees. So if the measure of angle E equals 45 degrees and these two polygons are similar polygons, that means the measure of angle E prime also has to be 45 degrees, since corresponding angles are congruent between similar polygons. So the measure of angle E prime would also be 45 degrees. Okay. What do they want us to find next? Alright, so this time we're going to find UN. We are going to find side UN. Okay? So how are we going to find the missing side? Well, what you're going to do is, to find a missing side, you set up your proportion. How you do that is you're going to take your scale factor, which would be 4 to 5, set that equal to, because between this quadrilateral and this one there's a scale factor of 4 to 5. You'll set that equal to UN of the first quadrilateral over 15 of the second quadrilateral, okay? So then you have the proportion 4 to 5 is equal to UN over 15. Which would have to mean that 5 UN is equal to 4 times 15, which is 60, which simply means that UN would have a length of 12. So UN has a length of 12. We could determine that. UN has a length of 12. Alright. This time we're going to find T prime U prime. So we're being asked to find T prime U prime. So let's start out, let's take our scale factor of 4 to 5, right? Set that equal to your value of TU, which would be 16, over your corresponding side of the second quadrilateral, which would be T prime U prime. So then you multiply the cross products and do all that, you should end up getting 4T prime U prime equals 5 times 16, which would be 80. Which then could only mean that T prime U prime would have to equal 20. So the length of T prime U prime is therefore 20. right, let's see here. Find TE. So we're going to find the length of side TE. Well, again, start out with your scale factor, your 4 to 5, set that equal to the TE, which we're trying to solve for. So the scale factor reflects first the left quadrilateral, the bottom one in the denominator reflects the second quadrilateral. So therefore you want to set it equal to the value of the first quadrilateral that you're trying to find, which in this case would be TE, over that T prime E prime, which has a length of 5K. So if we do the proportions, you would get that 5 TE has a length of, is rather equal to 4 times 5K, which would be 20K. Which would have to mean then that TE would have a length of 4K. So the length of side TE would equal 4K. And then I have a very useful problem here. You know what? I should have kept it. Oh well. So this is 4K, 28, 35. Shoot. Let me find T prime here, U prime, because we're going to figure out next the scale factor of the perimeters of each quadrilateral. Okay? So let's see. 4 to 5 is equal to 16 over T prime U prime, which would have, yep, so TU would have to equal 20. Okay. TU is T prime U prime is 20. And then 4 to 5 equals UN. Oh, that's right, that was 12. Okay, there we go. So now we are going to find the scale factor of the perimeters. I think you're going to find this very interesting. We are out to find the scale factor of the perimeters. Well, let's find the perimeter of quadrilateral TUNE. So, perimeter of TUNE, that's going to equal what? 28 plus 12 plus 16 plus 4K, because all you do is you add up the sides together, right? Which means the perimeter of tune is going to be 40, 56, so you would end up getting 4K plus 56. So the perimeter of the first quadrilateral is 4K plus 56. Let's find the perimeter of... Actually, I think we got a handle on the scale factor of what the quadrilaterals are. Let's focus on the perimeter, okay? So this perimeter is 4K plus 56. Now how about the perimeter of T prime, U prime, N prime, E prime? Again, add up the sides together. So you'll get 35 plus 15 plus 20 plus 5K, which is going to be equal to, that'd be 50, 70, all right, so that'd be equal to 5K plus 70. So now we have the perimeter of TUNE is 4K plus 56. The perimeter of T prime, U prime, N prime, E prime is 5K plus 70. So let's go ahead now let's find the scale factor of the perimeters. You'll take the 4K plus 56 all over the 5K plus 70, which in each of these we can factor out. In the numerator, we can factor out a common 4, which would end up being 4 times the quantity of K plus 14. In the denominator, we can factor out a common 5, which would give you 5 times the quantity of K plus 14. So the ratio of the perimeter so far is 4 times the quantity of K plus 14 over 5 times the quantity of K plus 14. Well, the K plus 14s will cancel out. That means the scale factor for the perimeters is also 4 to 5. In fact, this is a very important thing to teach you now. So whenever you're dealing with any polygon and you need to find the scale factor of perimeters, it's the exact same as the scale factor of two corresponding sides between the two quadrilateral, or between the two polygons. So if you know the scale factor of corresponding sides between the two polygons, that will also be the scale factor of your perimeters. Now, a little later in the course, we'll talk about the scale factor of areas and volumes, which are definitely different than what we're talking about today. But that's for another lesson. But just know that the scale factor of the perimeter will be the exact, of the perimeters will be the exact same as the scale factor of your sides of both corresponding polygons. Okay. Just got a few more here. I got 4 more problems. So this time, whoops, I want to draw in black. Excuse me. I find it easier to draw in black. Okay. Let's go ahead and make that mark. Oh no, it's straighter. All right. What's the next one? This one stands upright. This one actually slants up a little bit. Then the next one, this is actually a good example to show you here. So this is going to slant up. Trying to draw these in reverse is a bit tricky sometimes. All right. So for sure we are going to be given 2 similar quadrilaterals. I mean 2 similar polygons. So 15, 27, 18, 21, we get similar angles here. We got Y, Z, 20, and X. Okay, and then this time we have it backwards. So these are 2 similar polygons. The goal is going to be to find the values of X, Y, and Z. So if they're similar, all the sides have the same scale factor and all of the corresponding angles are congruent. You can see though that one is just the mirror image of the other. They're flipped around. That's all it is. They were flipped around. So let's go ahead here. Let's start by finding our scale factor between the two. So This side has a length of 18, right? This side here has a, well, wait a minute. See, this is why you got to pay attention to corresponding sides. You would think this side would match up with this side, but if you look, they're flipped around from each other. So actually 15, that slanted side would correspond to the 20, the slanted side on this one. Well, 15 to 20, that reduces down to what? 3 to 4. So 3 to 4 is now your scale factor. It's always important to identify your scale factor in these type of problems. Now from there, we can go ahead and solve for the missing side. So let's find x. First, take your scale factor, set that equal to, since the scale factor is based on this quadrilateral before this one, that means you're going to take the corresponding side of this quadrilateral, which would be 21, over the corresponding side of that quadrilateral, which would be x. So you'd have 3 to 4 is equal to 21 to x, which would then give you that 3x equals 84. Which would then only give you that x is equal to 28. So x is equal to 28. Now we need to solve for y. So again, take your scale factor of 3 to 4, set that equal to first the corresponding side to y, which here would be 18. You start with your left quadrilateral, since the scale factor is based on the left quadrilateral to right quadrilateral. You'll set the 3/4 equal to 18 over y, which would then give you that 3y is equal to, what's 18 times 4? That would be 72, which would have to mean then that y equals 24. So far we've identified x having a length of 28, y being a length of 24. Now we just need to find z. Again, start out with your scale factor of 3 to 4. Set that equal to, in this case, that'd be 27 over z, which would have to mean then that 3z is equal to 27 times 4, so 50 would be 108. So 3z is equal to 108, which would then have to mean that z, so 108 divided by 3, so 33, 34, 35, 36. So z would have a length of 36. So in this case, you should get x equals 28, y equals 24, and z equals 36. I got 3 more problems, then we're done. Alright. 2 more similar polygons here. So smaller. In this case, we have pentagons. So we have 2 similar pentagons. Now, what else are we given? Let's start with identifying our congruent angles here. So this time nothing's flipped around, which is nice. This will be 18y 12 15. And what's in the next one? Zx 10 and 12. Okay, so this time, based on the way the corresponding angles are aligned of these similar pentagons, everything is in their proper place this time. Nothing's flipped, so it's going to make this problem a lot easier. So first, before we solve for x, y, or z, it's going to help to find our scale factor. In this case, on the left pentagon, the 15 corresponds to 10 on the right pentagon. So 15 to 10, that's going to reduce to 3 to 2 for your scale factor. So your scale factor is in fact 3 to 2 in this case. Now, let's solve for x. Of course, take your scale factor of 3 to 2, set that equal to, we want to solve for x, so the 12 is going to come first since the scale factor is based off of the left quadrilateral first. You'll put your 12 in the numerator over your x in the denominator, which would then give you that 3x equals 24, which means that x equals 8. So the value of x that we should get is 8. Now let's do the solve for y. Once again, start with your 3 to 2 scale factor. This time y is on the first quadrilateral, so that means y will come in the numerator of the second ratio, and then 12 will come in the denominator of the second ratio. So you'll have the proportion 3 to 2 is equal to y to 12, which should give you that 2y equals 36, which should then give you that y is equal to 18. So we got a value of y being 18. Now let's solve for z. Again, take your scale factor of 3 to 2, set that equal to, we want to solve for z, so the corresponding side on the first quadrilateral to z has the length of 18. That'll be equal to 18 to z, which will then just give you that 3z equals 36, which would have to mean that z equals 12. So for this one, you should get x equals 8, y equals 18, z equals 12 for these two similar pentagons. I got two more problems and we're done. We got, oh, good one. This is good. We're going to be working with triangles a lot here in the near future, especially right triangles. We're really going to be working with them. Oh, that sucked. That's rounded. It's a good thing I'm not an art teacher. Oh boy. Alright. So let's see. Right angle here, right angle here. Okay. 12 times the square root of 3. This is a 60-degree angle here. Alright, this has a length of y. This is x degrees, so we're actually going to solve for degrees for x. So this has a length of 40. Alright, z and 20. Okay. So we've got all our parts and pieces labeled. Now, again, first thing you want to do, find your scale factor. The only thing we can conclude for sure with each of these is you have 12 to 20. Only one pair of corresponding sides both have actual numerical values. So we'll take the left one, the 12, to the 20. 12 to 20 reduces down to 3 to 5. So your scale factor is going to be 3 to 5 between the left triangle and the right triangle. So now let's find x. X is a degree measure, right? You can see that one triangle's flipped from the other. So basically here we have the 90-degree angles. So on the left one, south of the 90-degree angle, we have 60 degrees, which means since they're flipped, the 60-degree angle would actually have to be up here since they're flipped. And we know that the acute angles of a right triangle are complementary. So 90 minus 60 means x equals 30. So x would be 30 degrees, okay? Now we need to solve for y. Well, of course, since you're solving for the length of a side, y, you're going to take your scale factor of 3 to 5. Okay, set that equal to, you want to solve for y, so y, the scale factor represents the first triangle to the second triangle. So in this case, you'll set it equal to y on the first triangle over the corresponding side on the second triangle, which is 40. So you'll end up with 3 to 5 is equal to y to 40, which would then give you that 5y equals 120, which could only mean then that y equals 24. So in this case, you get a value of y being 24. Now let's go ahead and find z. This one's going to be fun. You still take 3 to 5, set that equal to, well, this time it's obvious the longer leg of the first triangle corresponds to the z here on the second triangle. Like your scale factor is the small triangle to the bigger triangle. So you're actually going to take 3 to 5, set that equal to 12 times the square root of 3 all over z. It's fun since we get a radical, which would give you that 3z is equal to 5 times 12 times the square root of 3, which would give you 60 times the square root of 3, which means that z equals 20 times the square root of 3. So the values you should have gotten here are going to be x being 30 degrees, y being a length of 24, z having a length of 20 times the square root of 3. And I got just one more problem. This one's a really interesting one too. This will prepare us for what's to come next with similar shapes. Alright, last problem. I better draw this one big actually, because, well, you'll see why in just a minute here. Okay, we got that. Now it should become apparent why I drew it kind of big. Alright, so let's see. We have a right angle. We have a right angle here. So this is x, y, z. This has a length of 10. Just this segment has a length of 14. Alright, this whole thing here has a length of 15. And then, see, up here has a length of 16. And then to the right has a length of 12. Okay. So what we have here to behold is very interesting. We have two quadrilaterals really in one. We have the big quadrilateral, and inside of it we have a similar quadrilateral to the big one that's smaller. So sometimes this will occur. So in other words, we're going to find the scale factor of the smaller quadrilateral to the whole thing. So I think what we should do first, the only thing we have here to compare is that in the smaller quadrilateral, the bottom base has a length of 10. And then on the big whole quadrilateral, the part excluding the smaller has a length of 14. So obviously, we're going to want to add these two together to get the entire length. So the entire length of the bottom base of the whole quadrilateral is 24, right? 10 plus 14 equals 24. Okay. So to find the scale factor, we're going to take the base of the smaller quadrilateral, 10, to the base of the entire big quadrilateral that's inside of, 24. So you'll actually have the ratio of 10 to 24, which would end up giving you 5 to 12. So the scale factor between these two quadrilaterals is actually 5 to 12. Then we can proceed from there and find x, y, and z. So whenever you have, let's say you have technically two quadrilaterals, or it don't matter what type of polygon it is, you have one inside the other, it's going to be the ratio of the small, your scale factor will be the ratio of the small polygon to the whole polygon that it's inside of. So let's find the value of x. Well, we have the ratio 5 to 12 for the smaller polygon to the entire thing, which means that you're going to set the x in the numerator of your second ratio to the 15 for the length of the whole thing on the left side, which is going to now give you that 12x is equal to 75. And yes, you're going to get decimals sometimes. That can sometimes happen. If you divide both sides by x, you'll get 75 twelfths, which we know is going to be 6 and 3 twelfths, in other words 6 and 1/4, so x would actually have a value of 6.25. So x is equal to 6.25. Now let's find the value of y. Again, you have the scale factor 5 to 12 for the small quadrilateral to the whole entire thing. So you're going to set y in the numerator to the value of the top base of the whole thing, which would be 16. So you have 5 to 12 is equal to y to 16. This means 12y equals 80, which would mean y is equal to 80 over 12. So 12 times 6 is 72. 12 times 7 is 84. So that's going to be 6 and 8 twelfths, 6 and 2/3. So you would get approximately 6.67. So y, if we round to 2 decimal places, is approximately 6.67. And then we want to find z. It's going to be the same process. You'll take your 5 to 12, set that equal to the z over the length of the right side of the whole thing, which would be 12. Which then means that 12z is going to equal 12 times 5, which is 60, which means z equals 5. So yes, sometimes you actually can get decimal answers. You should get that x is equal to 6.25, y equals 6.67, and then z equals 5. So that's been it for this lesson. The next lesson we are going to talk about similar triangles. We're going to talk about a postulate for them. That's going to make it easier to tell if they're similar. So I hope everyone has a great night. Take care.